All right, hello everyone. It's January the 11th. All right, so we're gonna do this first, and after that, we're gonna redo this. Okay, we're gonna redo this because the brute force method that we saw on the discussion we didn't try, so we want to try that. Overall, I think it should be very similar in the performance, but the implementation is much easier. All right, let's do this one first. Number of nodes in the subtree with the same label. Given a tree consisting of n nodes numbered from 0 to n minus 1 and exactly n minus 1 edges. The root of the tree is node 0, and each node of the tree has a label, which is a lowercase character given in the string labels. The edges, we have an array. Return an array size of n, where answer I is the number of nodes in the subtree of the ith node, which has the same label as node I. So label A has 2. Okay, so that should be 1, right? That should be 1, 1, 1, 1, 1. 4, 2, 1, 1. 3, 2, 1, 1, 1. Okay. So basically, we just at each node we want to know how many is in there. It could be like a counter, right? Yeah. So everyone will return a counter, and that shall do. And I didn't give it too much thought, but I think if we at each one we just return a counter, it shall work. Right? It shall work. No, counter. And graph. What do we return? We return a counter. So at each one, we're gonna have its counter. So rest is gonna be a counter, right? And then rest labels index plus equal 1, right? Because I need to count myself. And then for next in graph index, if next is not equal to parent, then DFS next in index rest plus equal to this, and I return rest. Okay, but before we do that, we need to have the result. 0 times, right, times n. If we do that, we're going to say, oof. Okay, say res what? Index plus equal to current labels index. And now we say DFS 0 minus 1, and then we'll return res. I shall do, right? We got a total, and then we incorporate everything in our return. And this will just be the number of counts. Right, this is the number of counts. Actually, I think that equal will be sufficient. It's the number of counts for the current label. Okay, let's give this a shot. count subtree. Okay, looks to be good. Huh. They're kind of slow, but yeah, no intention to change. I mean, yeah, because I return a counter, so this process can be slow. You can just, you know, it's more explicit. It's better than implicit. O26N. Well, we could call it ON. Yep, so you have to do this. That's what you need to do. Okay. Done. All right, we're gonna do this again. All right. Brute force. Go from partition 1 to the go from one partition until the desired number of partitions. At each partition, we can compute the total, right? The total length. All right, we compute the total length and compare that to the max length possible. And we stop when a fit has been encountered. Right, so I'm gonna say for k, now k equals 1, right, because of one partition, while true, so the total length, right, total length, I don't want to recompute the total length, as you can compute the total length, and then once you get a new one, but how do you, yeah, like if we have say 10, right, and then I have 11, you basically just add 11, 12 until you go beyond, right, until you go beyond to 3 digits, then you have to add more. I don't remember how they do it. We can just do digits, right? Number of digits, additional digit. So if len message, right? While true, we say the total length, current length, right? And every time current length plus equal to, if we add a new one, all right, the new one we need 3 plus 2 times k, right? Because we add a new one, 3 plus 2 times k. Then we need to also add something times the number of partitions, right? So k minus 1, right? The number of partitions. And this is if we have a change in the digits. So we say len str k minus len str k minus 1. All right, so this is the current length. And we say if current length is smaller or equal to limit times k, I'm gonna break. Otherwise, current length is larger than, then we say k need to plus equal 1. And then we keep going, keep going. At a certain point, how does impossible get encountered? I'm trying to think. Not times k, it's times len str k. Right, so keep going. At a certain point, if it's smaller, actually, that's a good question. I don't know. Let's see. I have 2, 1. Oh, we don't have impossible. Yeah, what if limit is small? Yep. So we need to figure out how. So what's going to happen in this case? This is just going to be larger than. And no matter how, it's going to be larger than. And how do we know? Or we say if the limit is as long as it's larger than 5. If it's larger than, if it's larger than 5. Yeah, that's not true. So it should be the current. This is right. While this is actually, I say while true. Occupied should be this. All right, when you say if occupy is larger or equal to limit, then we should return this. That means it's not possible. Otherwise, we can do this. Yep. Let's consider these two are equal. Yeah, as long as occupied is smaller than limit, we can always just add 1. So it'll always work. Can we do something like this? Yes, I can. Okay, then we're gonna just do for range 1 to k plus 1, right? For each one rest append something. Append what? Append all right, we have this. That will be k. This will be I. All right. What about this? Well, that's what we can do is I2, no, that's not I. So I'll do a j. J is 0. Okay. I know what, let's do this as a j. This is I. This will be j. And then to take minus 3 minus len strk j. Right, so this is gonna be message j towards j plus to take. Actually, I'm gonna do all the way to k, and then no I plus equal to take. At the end, rest append the last one. Okay. I towards the end. Then I'll return rest. See? I think it works. Yep, doesn't seem to be any. Yeah, this is actually very easy if you realize that we can just brute force. I feel still a little bit different compared to his brute force. Oh yeah, I don't have to. That's true. We don't need this because this will be outside. It'll be the same. Okay, so we're done with this. Okay, now we can close all of this. Okay. Oof. Huh, we solved the easy one already. Maximum sum of distinct subarrays with length k. Find the maximum subarray sum of all the subarrays of nums that meet the following conditions. The length of the subarray is k and all the elements are distinct. Return the maximum subarray sum of all the subarrays that meet the condition. So what we're gonna do is, that's just asking for a sliding window, right? That's just asking for a sliding window. And we just need to make sure that nothing is repeated. K is Lord. We need to set up a set. Yeah, we set up a set. Okay, so we have a set, and then we say the length of the set, and then we just remove and add. Yep, that's actually not difficult at all. Good. I think as we get this done, we shall be able to finish 30 minutes. We need a set, right? So what we can do, I want a first k. So we say max, we say res equals sum nums the first k, okay? And then unique is me set nums first k, right? And then, it depends on if it, if len unique is equal to k, else we want a maximum, right? So 0. Then for I in range from k all the way to len nums, right? So what do? We say unique dot remove nums I minus k, right? And then unique dot add nums I, and then if len unique is equal to k, then res, we need a sum no matter what. Current sum equals this. Right? Then if this, then, no matter what, we need to do this. Current sum plus equal to nums I minus k. So we need to do this no matter what, right? And if this res equals maximum res and current sum, blah blah blah, return res. Okay, that shall do. Yep. Ugh. The hell? Too fast, man. Too fast. Oh, you're here, right? So we remove. So I'm pointing here. Remove this. Oh, shoot. Dang it. 15, yeah, it's 24. Forgot. Yeah, that's true. That is absolutely true. That's no good. I have to check for this first. Oh, wow. Okay, this is unexpected. What? How? Shoot. Yo, this is bad. No, if this is in, then we're gonna remove. After we remove it, Lord. Okay, hold on. So I'm gonna remove it, right? It's a little bit more complicated than I had expected. Yeah, because then unique is only one. Like one have a one. Then you move down, and then yeah. So this is a one. This is now good. But when we do this, right? We move down because 9 is already removed. So I'm adding this. Huh. Hold up. So this definitely we're gonna remove, right? But if that's the unique one, which means if we say, okay, the previous is a unique value in the previous window. Now I move forward, now I remove one. And if I remove one, causing this, I just, no, hold on. Yeah, unique is only one, we only have one value, right? So that's no good. So next, now this is init, so I remove it. So now unique is empty, and add ones only have one value. That's not true, right? That is actually not true. That is actually not true. Damn, man. Because what we don't want is consecutive. Yeah, what if we have those? Right, you remove it, but actually there's one more inside. Holy moly. Yeah, I don't think that's the right way to do though. I do think we need a counter. And this is not, it's not working. Damn. Okay, so now we can do, now it doesn't really matter. Okay, we should say if, no, counter nums I minus k minus equal 1. If not counter nums minus k, then we remove, right? And then unique dot add, and then counter nums I plus equal 1. Then do this and do this and do this. I thought we can avoid counter. But turns out my solution requires counter. Unfortunate. Well, I thought I could do it without using counter, but that is not possible because we need to know when the unique set is okay to ditch a value. That only happens when the set value has 0 count. Well, still on, but I guess it's fine. Oh, maybe we can use map. Oh, well, we're not using map. We can use maybe. Oh, in this we don't need this length. Yes, I don't know why you don't use this. Counter. You can do counter here. Counter this. If not, del counter nums. There we go. That's the one. Don't need this. Do this, and then this is gonna be counter. Yep. Just use counter. I think I was doing it. Think about it wrong. Counter itself is sufficient. More than sufficient. Kind of 1 millisecond. Alright, that's it. It's a little bit over 30 minutes, but that's okay. I'll see you guys tomorrow. Adios.